Good morning. I'm Jaeheung from Seoul National University, South Korea. My title today is Compliant and Precise Control of Vital Robot. Okay. So two-leg robots typically have feet to support full body motion, probably for music. And because of that, the leg is typically heavy, and also ankle is quite weak compared to that. And with this, this is I think one of the typical characteristics of two-leg robot compared to four-leg robots. And with this robot, we want to provide compliance when we walk due to the uncertainties of the ground. And also, we sometimes provide precise control and speed control of the leg for ventilation or some locomotion on stairs. And in our lab, we have been working with position control robot and also torque control robot. And I want to share our experience with you today. And the position control robot, which is supposed to be precise, and we want to provide compliance. And also, the torque control robot, on the other hand, is inherently compliant. But in our lab, our robot had the trouble improving motion control performance. So we wanted to improve on both sides and try to use position control robot and torque control robot and see the difference. So these are the topics that I want to share with you today. And we implemented disturbance observer on each joint of the leg, and estimated external force using theory, and then used the information to rotate the joint in the same direction as the disturbance. So this is a bit opposite application of typical DOB, and you can see that it could deal with some unknown objects on the feet, and also it could deal with large disturbance on the upper body. And this is the diagram, plus diagram of implementation. You can see that this plus is the important thing, that we rotate in the same direction, then we can provide compliance instead of disturbance rejection. And then later, we also try to use momentum observer, which is quite similar to DOB. And the problem of using MOB was that it was difficult to differentiate external torque from uncertainty torques due to the model design. So we tried to implement LSTM network to learn uncertainty torques in free space motion only, and then we trained in free space, and then we subtracted this trained uncertainty torques from MOB torque when we had a collision. And with this algorithm, we were very successful detecting collision, but we found out that not only doing that, we could quite accurately estimate the external torque. So now, in our lab, right now, we implement this algorithm on two-leg robot, and it's quite working very well. So we are writing a paper right now, and probably next year I can share with you the result with the video. And now moving on to the torque control robot. So we have this two-leg robot, and then this was built to the humanoid robot later. And we implemented the operational space control framework on this torque control robot. And torque control robot is supposed to be compliant, so you can see this compliant motion, stepping on unknown objects and reactive walking. All of this was possible without any force torque sensors on the feet or anywhere. And now we had some problem of improving position control accuracy with this torque control robot. And we tried to find out all the reasons, and these are the list of them. And we found that the top two was the main problem for our robot, joint compliance and actual. So we wanted to deal with this problem. And for compliance, we had this kind of modeling, and in the feedback of the position control, we used only lower side information and neglecting the inside information, and it was quite successful. And then for the bandwidth problem, so the typical bandwidth problem that we noticed was that when we increase the bandwidth of the task space, then it requires the same bandwidth on the torque space. But some of the joints have less performance than the others. So that was really the limitation of the increasing bandwidth of the task space. So what we have done is that we do the stepwise control that at the beginning we just set up low gain to the task space, and we use all the joints. And then when we increase, we use only some of the joints that has high performance. And then this is step 2 or 3, we could improve a lot, and you cannot see the difference very well. Unfortunately, in the movie, if you look at the robot, then it's much better, and also in the graph, you can see that quite good performance. So lastly, so we also worked on learning, and we wanted to implement use of torque control directly. So this, the upper one, is the very typical implementation of reinforcement learning using position controller. There, usually they have PD control or PID control or some gains to control position. And then they try to learn code to walk. And in that case, what people do is that they do RL, and then if they don't work very well, then they come back, tune the gains, and then do it like iteratively, and then until it works. However, if we remove that, and we directly learn torques, then we don't have to do that step. So it's much cleaner and faster, and not necessarily faster, though. And then it was quite good. And another thing is that we have very robustness to the reality gap due to the inherent compliance. So this was the video that we had, and it was working very nicely. And we submitted the paper with that, so you can actually look at this paper in the archive right now. So I can take questions now, while you can watch our nice video using humanoid robot. Walking quite slow, but it's the amateur system. You can see.
We have 2 minutes for questions, I'm sorry.
When you're learning with torque outputs, what's your control frequency and what's your exploration? Like, how do you do exploration?
How do I?
What's the control frequency when you're doing torque as your output, and how do you add noise? Like, how do you do exploration?
Okay, so for this question, right? So we, so for the first question, we tried actually quite different frequencies, and it was quite interesting that the lowest was 60 hertz and 62.5 actually with the real system, and you cannot notice actually. So this is one direction that I want to investigate more, because that means we can probably control the robot with 62.5 hertz, finally, very, very low frequency. Then you can save a lot of energy and a lot of effort in the electronics. Right? This is quite interesting. And when we learn in simulation first, and with dynamic randomizations. So we vary the inertia, link lengths, and many things. That's your second catcher, right?
Yeah, you're just doing white noise for your policy.
No, we changed. Yeah. Gaussian.
So here you mentioned like the required PDK's tuning. It means the offline tuning and constant in during the control period or online modeling?
That's what we usually.
Okay.
And we did the same thing.
Okay.
So we fix the game and then train. If it doesn't work, then you go back and you fix another game and then train again until it works.
Okay.
That's usual.
One question is about the reinforcement learning for the torque control, torque command. So you already have the reference joint motion, is that right?
Yes.
Okay.
So we created reference motion using normal other type, but so this is one of the costs actually. So there are like speed and other things. So this is like roughly following the motion, not exactly.
Another question is about, you mentioned the DOB, but the DOB consists of 2 parts. The first part you calculate from a feedback term, and then another term is learned by LSTM and then neural network, is that right?
So LSTM is MOV, DOB is separate.
Ah,
Yeah, so it's a separate implementation, but similar concept.
but actually I wondering the LSTM, so which the rule, the LSTM play. I mean, it's kind of you learn the model, it's kind of feed forwards. I'm not really understand.
So basically, there's a modeling error, right? If you move around, then you can estimate that in free space, and that exists all the time, right? So when you hit, then you can actually take them out, and then you estimate only some of those. So actually, now we could actually remove the force scope sensor, right? And then we can estimate quite accurately with this model, actually, the ZMP and everything. So it's quite nice. So this is what we are working on right now.
Okay.
Thank you very much.